So last class we did discussed about semaphore and then mailbox. Semaphore, what is the use of semaphore we are using? If you are, if you want to access that, multiple processes want to access the same interface, or multiple processes want to do the same operation, like write operation or read operation. Without completion of the write, we are doing a read operation. Then race conditions may occur. To avoid the race conditions, we will use this semaphore. Semaphore is like a keys. We have get keys and put keys. So based on the keys, it will operate the different processes. And mailbox. Mailbox is the inter-process communication class. Okay, inbuilt mailbox is the inbuilt class for your system Verilog. Okay, so it is used to communicate between the two components like generator and monitor. Okay, generator and driver. For this, we are using this mailbox. Mailbox is like a container. Okay, it can't define, it can't know the what data inside there. Just it is the work is used to pass the data from one component to other component. Okay, so here also generic mailbox is there and parameterized mailbox is there. Okay, and also we have different type of operation, blocking operations and non-blocking operations. Put, get, peek, and try put, and try peek. These are the non-blocking operations. Okay, so today we will discuss about system verilog interface. What is meant by interface? So basically, if we are having module input output ports, right? How we are communicating with the test bench through instantiation, either name-based instantiation or position-based instantiation. We are doing that. Okay. So just module name, what is your DUT name and user-defined name. Inside that, your signals like dot clock of clock, comma dot reset of reset, dot address of address, okay, dot data of data. That means DUT signal is communicating with the test bench signals. Okay. Now, if you want to add new signal in your module, okay, so you are updating the module. Okay, how we can write that? Again, I need to write entire module, right? And again, I want to instantiate entire data. Okay, so that is the problem. Here, the interface grouping the all module input output ports. Okay, interface is used to group the different input output port signals. Then you have interface and I am having interface. Both the devices are communicating through interface. Okay, interface will taking care of that signals representation. Okay, so how we are connecting the signals? One without interface, one-on-one communication is needed. Okay, with the interface, so through interface we are passing. Okay, if you want to add another signal, you can add easily. Okay, that's what we are saying. Nancy. Room A is communicating with the room B. We have different wires here. Okay, so we have room A connection and room B connection. For that, we are using wire 1, wire 2, wire 3, different wires we are using, like input output ports. Input ports we are using different wires. Output ports we are using registers. Okay, so from that we are connecting the different signals, right? So for that purpose we are using the interface. Okay. And so how we are connecting that? Without interface, individually we are connecting. Okay. With the interface, in interface only all the signals will be connected. Okay. So that's what. Every time you need to use different wires. So if you want to add the new signals, you need to use that new wires and connect with them. Okay. That is the module ports we are connecting, right? So that is the module ports and then instantiations we are doing. Okay, So this instantiation and test bench connection, DUT connection, this becomes very difficult to maintain, right? So that's what we are using this interface. Interface is like a single cable bundle of signals. Okay, so combining all the signals. Now, if you want to add new signal in interface, we can add the new signal easily, right? So, but in module, we need to add the new signal and then communicate with the test bench and then change the signal connections and then we need to write the different values. All these things are very difficult to maintain. But in interface, if you want to add the new signal, you can add it. Simply, I'm passing the interface name only. Interface, interface name. You are using in interface many things you can connect there. Like input output ports we are connecting, and then mod ports we are using, clocking blocks we are using, and assertions we are connecting. All the things we can write in our interface. Okay. See, if you are connecting 20 signals individually but all the 20 signals you are writing in one interface, then this interface will be connecting all the signals at a time. Okay, so instead of passing 20 signals individually, you can pass one interface handle. Okay, how we are representing the interface handle? Interface. Suppose some app interface, I am taking that app interface. Inside that some clock at the rate posedge clock or negage clock we are using, or simply we are writing normal interface also. Inside that we are representing the signals like logic I am using. Why interface is only using the logic? Okay, so because of interface is connecting. Suppose you want to connect unknown values, or you want to pass the unknown values. Then if you use bit means bit is a two-state data type. It is not representing the unknown values. If you pass the unknown values means it gives that zero value only. Okay, so same way here, uh, logic is a post-state data type. Okay, if you want to pass unknown values, you need to represent that unknown values. Or simply we can say that logic is supporting both the procedural and continuous assignments, and then bit is used for only continuous assignments. Okay, sometimes we are representing the procedural assignment signals also. Okay, that will not support. Okay. So that's what we are using every signal with the logic only. We are not mentioning that that is an input signal or output signal, nothing. Okay, just we need to add the signals in our interface and then we can pass that interface handle to your DUT. Okay, if you want to, so in interface all the signals will be there. Okay, so that will be connected to different components. That's what we are taking the interface. See, so what is an interface? Interface is a container. Okay, that groups that related signals and tasks, functions, clocking blocks, assertions, modports. So into one reusable object, if we are passing all the signals, tasks, functions, clocking blocks, assertions, coverages, all the things are represented in your interface, then that interface handle you are passing to your components, it will be communicating with that signals, right? See how my test bench is communicating with that signals in transactions. I'm representing all the signals. Okay, through class handle, I'm getting the signals in your test bench, right? Same way here also the interface. So without interface, we need to connect all the signals like clock, reset, valid, address, data, ready. Okay, instantiate it. So DUT user defined name dot clock of clock dot reset dot valid of valid. All these signals we are instantiating. But simply with interface we are passing simple interface only. Like that means this is your DUT. Okay, so this is your DUT. The DUT is having different signals, and this is your test bench. Okay, through interface I'm passing the signals. This is my interface connection. So this is interface. Okay, interface may communicate with the TV. Okay, so here the DUT signals are all the DUT signals are there in your interface that should be passes to test bench, and test bench gives the output. So sorry, test bench gives the inputs and DUT gives the output. Okay, that's what. See, any adding the signals, adding one signal, you need to modify DUT, test bench, driver, monitor, instantiation, all the things will be modified. uh, Instead of that, you are taking interface name. Inside that clock reset valid address and then ready. So suppose you want to add some burst signal, or if you want to add some flag signal, or if you want to add some count signal. Okay, entire DUT need to change. Okay, but I'm not changing the entire DUT here, only I'm changing the interface. Okay, so if I want to add the signal in your DUT, you can add it, and then interface also add that. Okay, only one interface handle only I'm passing. So that's what. See, interface, we are having my interface. What is your interface name? My interface is the my class my interface name, and inside that logic A, B, C, and end interface we are writing. So in your interface, how we are representing that interface name of the interface, like ABB interface. Okay, inside that logic I'm connecting P clock. Okay, so P reset logic, P reset, and then P data. Okay, logic, P write. So in this way I can represent my signals, all the signals. So if you want to add pwdata, so that means write data you want to add, you can add it. Here only we can add it. Just pass the interface handle only. Same thing. So simple interface example, adder interface, I'm taking that A comma B comma sum. Then DUT instantiation, how we are passing that? Module, module name, and inside that interface I'm passing. Adder interface is my interface name. Okay, so adder interface is my interface name. For that, I'm taking handle called interface. That is your DUT interface name. Okay, so just you are calling the all signals through this handle only. Okay, then see how I am adding that in your addition. Assign sum equal to a plus b. Okay, through interface I am adding that interface dot sum plus, because we are calling the signals in your class. Okay, whatever the properties there in your class, and you are calling in your module. How we are calling? Class packet, int address, data, end class. Okay, and your module TB, class packet. So packet handle is PKT. So PKT handle, we are calling the properties. Okay, whatever the properties represented in your class, that will be called in your TB, right? So like packet dot address equal to some value, packet dot data equal to value. Okay, one value you are assigning, after some delay you are assigning another value, or you are randomizing that. Okay, object dot randomize, and then pkt dot randomize. We are so that means pkt dot randomize we are using. Then randomized values we are getting, right? Here also same. So through interface handle only we are getting all these signals. See, in your TB also, what you are instantiating? DUT instantiation is there. That means adder DUT, and then through interface we are representing. Okay, so interface only I am writing all the signals. See, interface handle only I am passing. This is my module name, and this is user defined name, and interface signals I am representing. Without interface, how we are instantiating? Same way, adder, and then some DUT. Inside that dot A of A, comma dot B of B, and dot sum of sum. In this way, we are instantiated. So then through interface handle only I am instantiating. And similarly, this is my interface name and interface handle IND. Okay. Then in my TB, I need to instantiate DUT and then interface. After that, some clock generation and reset generation. All the things we need to mention in your TB. Based on that, you will get different signals. Okay. So now parameterized interface. Like parameterized module you are considering, right? Some parameter width equal to value 8 and depth equal to value 16 and then address width equal to value 32. In this way you are parameterizing your module, right? Same way I can also parameterize my interface also. Okay. Parameter width. Okay. So this width you want to change it, then you can change here 64. Or in your TB, your interface is there. Okay, in that interface, parameterized interface you are representing, whatever the parameter you are writing, you can override it. How you are overriding that parameter? Like dot width of, so dot width of, previously 16 I am using. Okay, now you are overriding that dot width of 32. Okay, or dot width of 64. Okay, that means it will support 16, 32 and 64 also. Okay, you are not changing your DUT, not modifying your DUT, just you are changing the test bench. In test bench I am overriding my parameters. Okay, then without changing your DUT we can override that and it will support the different bits. Okay, that's what. Okay. So bus interface, some APB interface or bus interface. Okay, APB interface hash some parameter. Okay, width you are taking and type order also I can change, right? Some t equal to integer I can take that. Okay, so in t equal to integer you can take it. You are taking means instead of t you are taking integer. Instead of integer I can apply bit. I can apply byte, I can apply logic. Okay, data type also I will parameterize. Okay, so that's what. See here logic width minus 1 down to 0 address. That means this is the equivalent to 31 down to 0 of address. Okay, similarly data also 31 down to 0 of data. Okay, here I'm what it called instantiating my parameter. Okay, that parameter will be representing to that your signals. Okay, beside the signal you are representing the parameter width. Based on that the signal width will be defined. Okay, clear? That is the parameterized interface. And with clock also we can use that. Okay, so with clock I can interface that. That means an input logic clock. Okay, because we are taking at the rate posedge clock or at the rate negate clock, that is events, right? So waiting events. At every passage of the clock, we are observing our inputs changing and outputs how we are getting. Based on the clock only, I will know, okay, which inputs are getting and uh, which inputs are passing and what are the outputs we are getting. Right? So that's what we are looking here. Interface with clock, same thing. Nothing will be changed here. Just interface name, input, logic, clock. Okay, and then remaining signals we can represent here. And then instantiation also, we are instantiating bus interface of clock. Okay, so inside that we need to consider clock. Okay, So interface with the parameterization, interface with clocks, and interface with normal DUT signals. So you know that, okay? Interface is different, interconnect is different. Interface in between the two components, we are using this interface. So to communicate multiple interfaces, we need interconnect. Okay. So all these interfaces are connected to one wire, that is interconnect. Clear? They will ask you interface and interconnect. What is the difference between them? Interconnect is communicating with the different interfaces. Interface is communicating between the two components. Okay. And we have different DUT signals inside the interface. Okay. So interface inside the DUT. What is that inside the DUT? I already written that interface handle, and then inside that my module name. Inside that interface signals we are representing. That means whatever the signals are there, all the signals comes to that module. Okay. So that's what he is representing. That is ALU interface. That means module ALU. Inside that ALU, what is the signals are there? A, B, C, and A, B, and result. All the signals are represented in your module. Previously, how I am writing that module name, and then inside that input logic or input wire. Okay, A, input wire B, output reach some result. In this way, I have represented, right? Now I have changed that representation. Same way, interface with tasks. Okay, we can also represent different tasks. Inside the task, we can drive different signals. Task drive request. That drive request we can call in your field. Okay, you understood, right? Interface with tasks and all these things. So that's what driver request is the task name. Then request equal to 1 and request equal to 0. Like some reset equal to 1 and after 10 seconds delay, and I am representing that reset equal to 0. That means I am applying the reset condition. Okay. Interface with functions. Functions also we can add that interface. Interface name. Function name. Instead of that, you can add that interface name. Okay. My function integer add int a comma b and return that different values. Okay. So like result a plus b. Same way, I can apply that interface inside that function. Whatever that inside the interface, I can represent that function. That function will display the function will return the single value. Okay. Here, what it is returning? Some value. Okay. So add is the value return a plus b. Okay. So uses that display function display interface dot add comma 10 comma 20. Okay. So that means addition will be happening through interface. Now interface with clocking blocks. The next concept is called clocking blocks. So the clocking blocks will decide you that what type of signals we are representing. Like this clocking blocks before sampling and after sampling. What is the signals you are driving to your test bench and what type of signals we are getting from the TB. Okay, through clocking blocks we are representing that different signals. So driver and DUT update the signals at the same time, and then same clock edge we are using that. At that time we are getting the race condition, right? So this is my clock, posedge clock. Here only you are adding some driving the TB signals, and here only you are observing the DUT output. Same time I am applying the different signal for the same clock edge, then I may get race condition. provide that race condition, we are using this clocking blocks. Okay, so clocking blocks used for synchronization purpose, and we need to use different posedge clock. One posedge clock we are driving the signals, and another posedge clock we are uh, seeing the outputs. Okay, so TB we are driving the inputs, and DUT we are getting the outputs, and then next positive clock I'm seeing my outputs, or next negative clock I'm seeing my outputs. Then this race condition will be avoided. Okay, understood, right? So same thing without clocking blocks, driver writes that at t equal to 10, and then DUT samples at t equal to 10. That's what. At the same time, I'm driving the signal and then observing the output. So, phase condition may occur. Definitely it will occur. So, to avoid that, we are using this clocking blocks. Okay, driver writes that, and clocking block will gives you some delay. After that, DUT samples that. Okay, DUT samples means DUT getting the outputs. TB drives the inputs, and DUT samples the outputs. Okay. Before clock age, I am driving the signals. Okay. TB drives the signals. And after clock age, okay, your clocking block observing the DUT signals. Okay, sampling the outputs. Then the race condition will be avoided. In clocking block, we are having some default input signals and output signals. Default input 1 nanosecond, output 2 nanoseconds. That means every input it is taking 1 second delay, and every output we are getting after 2 seconds delay. Okay, I will show you in the next slides. Okay, upcoming slides. And mod ports, and interface also we are representing some mod ports. Mod ports means the names we are representing. Mod port, that means module ports. In module ports, which one is the input and which one is the output, we are differentiating the direction. Okay, TB is giving the inputs to the DUT. Okay, whatever the TB giving the inputs to the DUT, that will be treated as an output of test bench. Are you getting my point? Okay, and then DUT giving the outputs. Okay, whatever the DUT outputs, that will be treated as the inputs to the test bench. Clear? So that direction we will decide in your mod codes. Okay. So any module can modify anything. That means it is dangerous to restrict the access, right? So that is the reason we are using this mod ports. So this mod ports we can give the direction to the input signals and output signals. So who is driving the input signals and who is sampling the output signals. Okay. So that's what we are checking there. See, mod port driver. I will tell you this class only mod ports and then clocking blocks also. Mod ports, some driver. In this driver, output is the request. Okay, actually request is the input. We are requesting, but from the driver it will be treated as an output, because from the driver to DUT we are driving the signal. Okay, so that is the reason request is an output and grant is an input. Okay, who will grant that? DUT will grant that, but DUT grant is an output. Okay, but for driver it is an input. Yeah, and then modport DUT. So reverse operation. Here output is represented request. Here input is requested as an input. Okay, and then output will be grant. Reverse selection. Okay, for DUT request as an input, and then output is grant. In driver modports, output is a request. Okay, input is a grant. Reverse the directions. That's what using mod ports we are driving the signals. My master module driver, uh, we can drive that interface signals. Bus interface dot driver interface. Okay, bus interface your interface name, and then interface is the handle of your interface. Through driver, I am driving the interface. Okay, driver interface I am driving here. Okay. So why mod ports? Think of bank account. Without mod ports, everyone can read it and modify it, and then rewrite that values. With the mod ports, so the customer only read and write, and then authority also is there for manager. Manager also we can see the our account details, but he can't modify it, right? So auditor read only and admin full access. So that's what we are representing different signals in your mod ports. Okay. So with mod ports, customer can read and write. So we are depositing the money and withdrawing the money. Okay. And then admin like manager will see the all account details. Okay. If our concern is there, then we will modify it. Okay, he will send to different persons accounts money. Okay, so from our account to different other accounts we are sending the money through check or any card access. Okay, so that's what same concept is also applicable for the bond codes. This is the full ladder example. A, B, C are the inputs, sum and carry is the output. In interface I am representing all the signals with logic only. Okay, and then DUT signals, how we are representing the DUT, assigning the sum output. Interface dot A plus interface dot B is equals to interface dot sum. Okay, so that means sum and carry we are assigning here. Okay, how we are assigning the sum and carry? This is the sum output. Okay, interface dot A, interface dot B, interface dot C. Okay, you are adding the three values A equal to 1, B equal to 1 and C equal to 1. All the signals are added together, 1 1 we are getting. Then here sum output and this one is the carry output. So then we are concatenating these two, carry comma sum. Okay, so two values are getting at the same time. In TB, I'm interfacing, instantiating the interface and then DUT signals with interface. Then I'm passing the values randomly, dollar random I'm utilizing that. Okay, without random keyword, we can use the dollar random, randomly assigning the values. See this summary. Okay. How then virtual interface also is there. Okay, what is the use of virtual interface? We will explain that. Okay. Interface with sessions, interface with coverage, interface with some virtual interface, all these things. So simply, interface is a bundling of your DOT signals. Okay, so it is all the signals are keeping at one place. That is the interface. Okay. Mod ports. What is the use of mod ports? So module ports. That means what is the problem with the interface? Interface, if you are driving that DB signals and then DUT signals at a time, okay, so then one driver is there, it's not a problem. But in your DB, multiple drivers are there. Then all the drivers are connected to the same interface. Then we may get conflict. To avoid that conflict, we will go for this module ports. So module ports gives you the direction here. See, that's what he's saying, that before learning the mod ports, first understand the problem with interface. Okay, suppose interface is driving that multiple drivers. Mod port solves this one. Like TB drives that request and DUT drives that request. So then same interface will get the conflict. DUT is also driving the request at the same time and TP is also driving the request at the same time. Then this interface may get conflict. Because of multiple drivers, this interface may causing the conflict here. Okay, to avoid that, we are using this mod ports. Okay, like this interface, request and grant. DUTB and DUT both are driving at all the signals same time. So then we may get conflict. To avoid that conflict, we will use this mod ports. Okay, so that is the reason we go for the mod ports. Mod ports defines that which signals a module can access. Okay, so what are the type of signals can access by the DUT, and what type of signals can read and write by the TB. Okay, and what are the signals can read by the task and functions, and what type of task and functions we are calling in your module ports. All these things are explained by module codes. So that's what basically your bank account is there. In your bank account, customer can deposit and withdraw the money, and auditor only read only the data. So whatever the data we have, it can see only. So the cashier tells you in your account this much amount is there. If you want to send, then we will send you. So he's saying that same thing. Auditor we can say read only, and manager will have full access. Same thing here also. Mod ports is working on the interface same way. Okay, it will defines you who will read, who will write, or who is having full access. That will tell you the mod ports. Okay. So without mod ports, the driver is driving the read and write signals, and monitor is also seeing the reading and writing signals. Both are at a time we are driving the signals and reading the signals. Reading and writing happening at the same time means that is the problem. Then race condition may occur. Okay, so this with the mod ports, see, I am writing that input. Okay, input here I am writing here and reading the output. Then monitor read only. It can read only the signals. Okay, then DUT read the inputs and write the outputs with the safe way. So because of we are mentioning some direction to the interface. Okay, in interface we are representing the mod ports, and then that mod ports will tells you that who will drive the signals and who will receive the input signals. Okay, so how we are representing the mod ports here? Mod port name, and input signal list and output signal list. Then interface we are driving like this. Interface my interface name, and then logic signals we are representing that input output signals. Request is an input, grant is an output. Now this mod ports driver is driving the signals. See, this is my driver. Okay, here this driver is driving the request. This is the reason uh, output will be request will be acting like an output to the driver and input to the DUT. Okay. Now here I can represent mod ports DUT. Inside that, input is the request and output is the grant. Okay. This way I can represent the direction. Mod ports gives you the direction to the ports. Okay, in which direction we can drive the input and which direction we are receiving the output. Okay, and then grant is the input from the output to the DUT and input to the driver. Okay, so that is the reason. See here, grant is generated by the DUT. So for this DUT output signal and driver, it will be acts as an input. Okay, understood? So that defines the mod ports. See, same thing. In my adder, A, B is the inputs. Okay, sum is the output. That is the DUT signals. In DUT, I can represent in the same way. Mod ports, DUT, input A, input B, output sum. Okay, but in driver, we can reverse the direction. Okay, so in TB, see in TB or driver is also it is there in TB only. Okay, so in TB output A, output B, input sum, because see this is the direction. This is your TB and this is your DUT, and DUT we are driving the input signals. A, B are the input signals. That is the reason outputs to the TB. Okay, outputs from the TB. In TB, AB are the outputs because these are going out. The direction is going out and coming to the input to the DUT. That is the reason A, B are the inputs to the DUT. Okay, and here sum is the output from the DUT. Okay, so sum is the output from the DUT. This is all the signals represented as a mod ports DUT signals. Okay, and same signals, sum is the output from the DUT and input to the TB. Okay, so that is the reason input sum we are representing in TB and output AB are represented in a TB. Okay, and same way inputs are represented as an in AB in DUT and output is a sum. Clear? DUT signals and KB signals, how we are representing this mod ports. In DUT module, adder is the name and adder dot interface DUT interface. Then sum equal to interface dot A plus interface dot B. Similarly, carry also we can write that. Okay, here I am sum only considering. Okay, same thing. In TB also, how we are instantiating that adder interface INTF adder DUT and then initial begin interface dot TB dot A equal to 10 and then TB dot B equal to 20. Okay, this way I can represent that signals. Then dollar display sum we are representing. This is the simple TB with the mod ports. So this is the view actually what happens inside that mod ports. A is an output, B is an output, sum is an input. Then that is the TB can write A, write B and read sum. That is the representation. Internally it is looking like that. And for DUT writing the A and writing the B. Okay, sorry, reading A and reading B. Okay, from the TB. Okay, because DUT is getting the signals from the TB. That is reading. And sum is the writing to the TB. Okay, so that's what write is the sum. In this way, we can separate input output signals from the TB and the DUT. Okay, so now TB is writing the signals to the DUT. AB. DUT reading the signals from the TB. Okay, so then both are different operations. At a time, I can do that. Then race condition will be avoided. Okay, and DUT writing the sum output to the TB. TB reading the output from the DUT. Okay, so then the race condition will be avoided here. Why not declare directions inside the DUT? In DUT, all the signals, input output signals only we are representing. I am not representing any direction. This mod ports only giving the direction to this input output signals or DUT signals. Okay, so that's what with mod ports we can give the names like module adder, bus interface, and interface name. Here, nothing prevents that interface.a equal to some value because we are driving the signals from the TV. Okay, writing the signals to the DUT. Okay, so this mod ports prevents that misuse. Like TV is driving the signals and then reading the signals, or writing and reading, and DUT is also writing and reading. This will avoid this mod ports will avoid this misuses of writing and reading. Okay. Same thing. Huh? So mod ports DUT signals input A, and then mod ports DUT output A. Okay, so then both are allowed. Sometimes in-out signals are there. That means input for the DUT, output for the TV, and then that means bidirectional signals. Okay, so in your I2C, okay, SDA signal is there, right? This is the DUT and this is the TV. Okay, in this SDA signal is there bidirectional. Okay, so that's what I2C and SPI bidirectional buses are there. Okay, at that time the master we are representing that in out port. Okay, so in out port we are representing that mod port some master in out we are representing. Okay, so that means input to the DUT, output for the TV, and then output from the DUT, input to the TV. Okay, so that is the in out port we are representing. You know, pass by reference. What is that pass by reference? If you change the value, then the value also changing. And pass by value means, so this pass by value is not changing the value. See how the module ports are representing here? Request and grant. Output is the request, input is the grant for the driver, and same thing will be monitor. See, monitor and then DUT signals are representing same here. So how we are representing monitor input request and input request. See, monitor all the signals are inputs only. There is no output because it is observing the signals only. It is reading the signals only. It is not driving the signals. That is the reason in mod port monitor you are representing means all are inputs. Okay, input to the driver that is also acts as an input to the monitor. Output from the driver that is also acts as an input to the monitor. Okay, but DUT we can reverse that from the driver signals. What are the signals are there? We can reverse that. So mod ports with tasks also same way. Previously I have represented the task, right? Some driver request, driver reset. Okay, and mod ports with functions also. Mod ports and clocking blocks both are there. Clocking blocks we are using the signals some delays where we are sampling the input, where we are driving the output. Okay, so that's what we are changing the signals with the clocking blocks. And virtual interface also we are representing them. I will tell you virtual interface what is the reason we are going for the virtual interface. Okay, same thing. Driver, monitor, and then DUT. See, same signals I am representing here. Driver output is the request, input is the clock. For monitor, all are inputs. And then for DUT, this output will be acts as an input, and this input will be acts as an output for the DUT. Okay, same thing. Understood, right? Mod ports, how we are representing the mod ports. This takes 2 minutes. So clocking blocks. What is that clocking blocks and what is the need of clocking blocks in your uh, test bench? Okay. So clocking blocks. So suppose we are getting race conditions, right? Where we are getting the race condition, imagine DUT and test bench both are operating on same clock. Okay, so you are driving the signals from the DUT, and then your TB is also driving the same signals from the TB. Okay, on the same clock edge. Then we may get so race condition. To avoid that race condition, we are using this clocking blocks. Okay. Mod ports gives the direction to the module ports and clocking blocks avoid the race condition while DUT, imagine DUT and test bench both are uses the same clock. Like your DUT is also at the rate posedge clock we are having, and then the TB is also uses that at the rate posedge clock. Okay, same edge we are driving the DUT signals. That means DUT samples the inputs. Okay, DUT samples the input. TB drives the input, right? TB driving the inputs to the DUT, and DUT samples that inputs and producing the output, right? Sampling means getting the output. Driving means giving the input. Okay, that's good. See, the question is what which happens first? That means does DUT read old data or does read DUT new data? So then simulator may schedule them differently. This creates the race condition. That means I'm driving the some A equal to 10, and then next one is driving the A equal to 20. Which data I need to consider? On the same clock edge, you are driving the same values and different same signals or for different values. Then what I need to consider here? That gives you the conflict. Okay. So to avoid that conflict, see, we are using the clocking blocks. Simple example. So I'm conducting an exam. You are you are writing the exam. 9 o'clock I have provided, I have distributed the question paper. 9:05 only I have started, I said that okay, stop the exam. Just now I have distributed and then same time I am submitting the papers. Then what you are writing? Nothing you are writing, right? I need to give at least 3 hours. 9 o'clock I am giving the paper and 12 o'clock I need to collect the paper. Then you will write something. 9 o'clock only I am giving the paper and 9 o'clock only I am asking the paper means what you are writing. What you are writing. Then race condition may occur. You will be fight with me, right? So why you are giving why you are conducting the exam? Same time you are giving the paper and same time you are asking the paper. Then what is the reason to conduct the exam? Then you will fight each other, and then obviously you will give a winning the race, right? So that's what. Same thing here also. To avoid that race condition, we will use that clocking blocks. Okay, clocking block is a synchronization mechanism that tells to the simulator we are giving the inputs. Okay, when the input should be sampled and when the output should be driven. Okay, this skew will define you some delay, input skew and output skew. Okay, so clocking blocks is having the skew. So how much delay we are giving? That means skew. Okay, delay or skew both are same. Okay, so that's what we are saying that input skew and output skew. So something they are saying that. Okay, so that's what. See here, uh, this clocking block controlling the timing. DUT is driving the signals to the TB is driving the signals to the DUT that will samples, and then DUT giving the signals to the TB that means driving the signals. Okay, so that's what. See, Without clocking blocks, I am driving the request at the posedge clock. Okay, same posedge clock. TB is driving the request. Same request is producing the DUT. Okay, DUT is also samples this request at the same clock edge. This is my posedge clock. Okay, DUT is sampling the request. That means giving the output. Okay, and TB here only TB is drives that request. That means giving input to the DUT. At the same time, giving the input and producing the output, is that possible? Not possible, right? Then race condition may occur. So with the clocking block, TB drives the request. After clock age, DUT samples the signals. Okay. TB drives that signals after clock age. DUT samples the signals before the clock age. Okay. So that means here this is after the clock age. TB drives the signals. Here drives the signals. And here DUT samples the signals before clock age. Okay. Then this ambiguity will be removed and then race condition should be avoided. Okay. See, this is the basic syntax of the clocking block. Clocking block at the rate posedge clock, input signal 1, output signal 2, and clocking block. Same thing we will use in your test bench. Okay. So clocking block at the rate posedge clock, input is grant, output is request. That means input is sampled. So grant is sampled by the test bench. That means driving the signals to the DUT. And then request is driven by the test bench. Okay. So request we are driving and grant we are producing. Okay. So that's what reverse. Okay. Request is the input from the TB. That is the reason TB driving the signal. And grant is produced by the output from the DUT. That is the reason TB samples the grant. Okay. Sampling means output, driving means input. Okay. So inside the clocking block, directions is specified from the test bench perspective, not the DUT perspective. Okay. So remember, TB is driving the signals. Okay. TB samples the signals. That means TB is driving the inputs to the DUT and then TB getting the signals from the DUT. Okay. So getting the signals is that sampling, giving the input to the DUT is driving. Okay. Clear? So from TB perspective only, we are writing the clocking block signals. So clocking block request is an output, grant is an input to the TB. Okay. So TB drives the request here and TB samples the grant. Okay. So this is the representation, clocking events. How we are representing the clocking events? Posedge clock. Clocking block CB at the rate posedge clock. Or clocking block CB at the rate negedge clock. Okay. So that means based on the event, we are driving the signals and then sampling the signals. Okay. See, this is the default skew, clock skew. So how we are representing that? Default input is 2, output is 3. That means every input will be driven by 2 seconds delay. And then every output is sampled by 3 seconds delay. Okay, that's what. Input sampling 2 units before clock edge. Okay, and then TB, that means driving the signals driven the output driven 3 units after the edge. Okay, so this is the clock edge. Before the clock edge, sampling the signals, and after the clock edge driving the signals. Here 2 seconds delay is there, here 3 seconds delay is there. Okay, then I am avoiding the next condition, right? Okay, so why input skew? Suppose DUT changes that outputs exactly at the same clock edge, then we are getting the race condition. So that is the reason input skew is there. So without input skew, TB samples at the same time, then race condition will occur. With the skew, TB samples earlier and stable values will be guaranteed after the clock edge. Okay, so that delay will be represented. Okay, input delay and output delay. So without skew, DUT may read old value or new value, and with skew after clock edge, no race condition. So that is the simplest representation of the clocking blocks. Clocking blocks will define you the input skew and output skew. That means driving the signals and then sampling the signals will be the different delays. Okay. So this is the default example for the clocking block. Clocking block at the rate posedge block and then default input 1 and output 2. That means your input signals sampled at one clock edge, before one sample, and driving the signals after the two clock edges. Okay. So grant is sampled one unit before. Okay, and then request is driven 2 units after that. Okay. So that's what input is the grant and then output is the request. Same thing. Here also we can represent input 2 seconds delay grant and output we are getting 5 seconds, 5 time units delay. We are getting the output. Okay. That's what skew. Input skew and output skew. See, interface with clocking blocks. Same thing. Interface we are representing the signals, right? Same thing we are writing in the clocking blocks. Okay. So clocking block at the rate posedge clock, output is the request, input is the grant. In TB perspective, right? Because from the TB, request is an output, grant is an input. Because request is coming from the TB to the DUT, grant is coming from the DUT to the TB. Hmm. There is no delay, just the posedge clock we are represented, right? So then this clocking block will sample the signals before clock edge and drive the signals after the clock edge. Then race condition will be avoided. Okay, default it will take. Okay, without clocking blocks, we may get the conflict. Race will be race will be happening. So, okay. So this is the simple adder example, same signal, A, B, sum. It is represented in interface. Same interface, clocking blocks and mod ports also we can write that. Okay. With the clocking blocks and mod ports we can write that. Then the race condition fully avoided. See virtual interface with clocking block. Same thing, I can represent the virtual interface. Okay. Multiple clocking blocks like driver clocking block and then monitor clocking block. In mod ports, we can represent this clocking block. Just mod ports, how we are representing mod ports driver, input, some request, output grant we are representing, right? So instead of that, in clocking block driver, CB, driver CB, DRV CB. That means driver is driving the signals. Okay, that is related to TB, right? And monitor is also related to TB. Mod ports monitor clocking blocks. Okay, mon CB. In this way, we can represent that. I will show you. Maybe the code is not there. Understood, right? So what is the modports and clocking logs and then interface. Shall we continue? Virtual interface. Okay. So tomorrow we will see this virtual interface. Okay. Up to this you can read.